thousands of years, gold has fascinated humanity. Entire civilizations have risen because of it. Empires have fought wars to control it. People have crossed oceans, climbed mountains, and risked everything for the chance to find just a few ounces hidden beneath the earth. Even today, gold remains one of the most valuable natural resources. Every year, mining companies invest billions of dollars searching for new deposits. Yet, despite all our technology, finding gold is still incredibly difficult because gold doesn't come with a map. It doesn't glow beneath the ground, and it certainly doesn't leave behind a sign saying, dig here. Instead, geologists spend years studying landscapes, collecting thousands of rock samples, mapping geological structures, and drilling deep into the earth, hoping that somewhere beneath their feet a valuable minerals deposit is waiting. Sometimes they spend millions of dollars only to discover absolutely nothing. Imagine investing $50 million, drilling hundreds of exploration holes, and finding no economically viable gold deposit. It happens far more often than you might think. So here's the question: what if there was another way? What if, before sending geologists into the field, before drilling the first hole, before spending millions of dollars, you already know where to look? Not exactly where gold is, but where the earth geology suggests it is the most likely to be hidden. It sounds like science fiction, but today something remarkable is happening. Artificial intelligence that is combined with satellite orbiting hundreds of the kilometer above the earth is helping geologists identify place that deserves closer investigation, not being seen underground, not by detecting gold directly, but by recognizing the subtle geological clues that most people would never notice. And those clues can sometimes be seen from space. That raises an incredible question: how can a satellite flying nearly several hundred kilometers above the Earth possibly help us searching for something buried deep underground? At first, the idea sounds impossible. After all, satellite can photograph cities, track hurricanes, monitor wildfires, measure sinking glaciers, and even detect tiny movement of the Earth's surface. But gold, hidden beneath the layers of the rock, surely that is impossible. Well, you're right. Satellite cannot see through solid rocks. They cannot photograph underground tunnels. And they cannot look beneath a mountain and point directly at a gold deposit. So, if that's true, why are some of the world's largest mining companies investing millions of dollars in the satellite imagery? Machine learning and deep learning or artificial intelligence? What do you know? The most people don't. The answer begins millions of years before human ever walked the earth, long before they were continents as we know them today. Before forests, before mammals, our planet was already creating gold. Deep beneath the Earth's surface, extremely heat, immense pressure, and mineral rich fluid were slowly shaping the deposit that modern geology is searching for today. And in doing so, the Earth left behind a series of hidden fingerprints. Fingerprints that have remained preserved for millions of years. Fingerprints that satellite can actually detect. But before we can understand how artificial source for gold, we first need to understand one of the geologist's greatest secret. Gold rarely travel alone. It always leaves a clue behind. And once you know how to recognize those clues, you stop looking for the gold itself and start looking for the story Earth left behind. Gold leaves clue behind, not piece of gold, not glittering veins visible from the sky, but something far more subtle. To understand these clues, we need to travel back millions of years to a time when the earth looked nothing like it does today. Deep beneath the surface, temperature reached hundreds of degrees Celsius. Water rich in dissolved minerals moved slowly through fracture in the earth crust, carrying elements such as silica, iron, sulfur, and sometimes gold. These weren't ordinary underground rivers. They were superheated hydrothermal fluids driven by volcanic activity and immense geological pressure. As these fluids migrated through cracks in the rock, something extraordinary happens. The surrounding rock began to change. Mineral dissolved, new mineral formed. The chemistry of this landscape was rewritten. Geologists call this process hydrothermal alternation. And although the gold itself often remain hidden deep underground, the altered rock remained near the surface, preserving the story of what had happened millions of years earlier. Think of it like footprint in fresh snow. Even if the person is long gone, the footprint remains. Gold deposit leave geological footprints, and those footprints are often much easier to detect than gold itself. But here's the fascinating part. How do geologists recognize these ancient fingerprints? The answer lies in something we experience every single day: light. Every morning, sunlight travels nearly 150 million kilometers from the sun before reaching Earth's surface. When that light strikes a rock, some wavelengths are absorbed and others are reflected back into the space. To our eyes, rocks may appear gray, brown, or the reddish, but our eyes are surprisingly limited. Human vision relies on just three broad color channels: red, green, and blue. Nature, however, tells a much richer story. Every minerals interact with the light in its own unique way. Iron oxide reflect light differently than clay minerals. Carbonates behave directly than silica-rich rocks. Every minerals that appear identical to the human eye can have completely different spectral signatures. Imagine every mineral has its own barcode, not printed with the black lines, but written in the light itself, invisible to us, yet unmistakable to the right instrument. This is where the satellite become something far more than cameras. Most people think satellites simply take photograph of the Earth, beautiful picture of the forest, mountain, oceans, and the cities. But modern Earth observation satellites are doing something much more sophisticated. They aren't just taking pictures; they are measuring the interaction between sunlight and the Earth's surface. Instead of recording only three colors, some satellite measures dozens or even hundreds of the individual wavelength. This technology is known as hyperspectral imaging. Think of a normal photograph as listening to a song with only three musical notes. Now imagine hearing every instrument separately: the drums, the violin, the piano, the guitar. Suddenly, the hidden details become obvious. That's exactly what hyperspectral imagery does. It separates light into hundreds of narrow wavelength bands, allowing the scientists to detect subtle chemical difference across the Earth's surface. Instead of asking what color is this rock, scientists can ask what minerals are likely present here, and that is an incredibly powerful difference because certain alternation minerals formed by ancient hypothermal system produce distinctive spectral signatures. These signatures do not guarantee the presence of gold, but they tell geologists something extremely important. At some point in the Earth history, this location experienced the kind of geological process capable of forming mineral deposits. In other words, the rock are telling us where to begin looking. This is why exploration geologists have relied on the spectral analysis for decades. But there is a problem. A single hyperspectral image can contain hundreds of spectral bands, millions of pixels, and billions of individual data points hidden somewhere inside the mountain of information. Maybe the geological clue that matter most. The challenge is not collecting the data anymore. The challenge is understanding it. And that's where artificial intelligence changes everything. Because would take a human team weeks or even months to analyze. An AI model can process in minute, but how does an artificial intelligence learn to recognize geological pattern that look experts decades to understand? That's the next piece of puzzle. For centuries, the greatest challenge in the mineral exploration wasn't collecting information, it was understanding it. Imagine someone hands you a library containing millions of books. Hidden somewhere inside that library uh, is a single page that could change everything. You know it's there. You just don't know where. That is exactly what modern mineral exploration look like. Every satellite image contains a extraordinary amount of information. Every geological map adds another layer. Every digital elevation model reveals subtle landforms. Every hyperspectral pixel contains hundreds of measurements. Every multispectral image contributes additional clue about vegetation, iron oxide, moisture, and exposed rock. Individually, each dataset tells only part of the story, but together they create something far more powerful, a digital representation of Earth geological history. The challenge is that no human can examine every pixel, compare every spectral signature, analyze every geological structure, and connect millions of relationships at once. The human brain is remarkable, but this is exactly the kind of problem artificial intelligence was created to solve. Artificial intelligence doesn't get tired. It doesn't lose concentration. It doesn't overlook pattern simply because there is too much data. Instead, it sorts for relationship hidden inside enormous data set. Not by guessing, not by magic, but by recognizing patterns. Think about how your brain recognizes a familiar face in a crowd. You don't consciously measure the distance between the eyes, the shape of the nose, or the curve of the jaw. Your brain has learned those patterns through experience. Artificial intelligence work in a surprisingly similar way. Except instead of learning face, it learns geological signatures. Instead of recognizing people, it recognizes environments where the mineral system are more likely to exist. But there is an important distinction. Artificial intelligence doesn't know what good gold look like beneath the ground because no satellite can see through solid rock. Instead, the AI learned to recognize the surface evidence left behind by the geological process that often accompany mineralization. It asks questions like these. Does this area contain alternation minerals commonly associated with hydrothermal activity? Do the spectral signature match non-alternation patterns? Are there geological structure capable of transporting mineral-rich fluids? Are there faults, fractures, or rock contacts that increase the likelihood of mineral deposition? How do these characteristics compare with places where the valuable mineral system have already been discovered? Each question alone means very little, but together they begin to tell a story written over millions of years. As the AI analyzes this information, it assigns different level of confidence to different location. Area with l- stronger supporting evidence receive high prospectivity score. Areas with weaker evidence receive lower score. The result isn't a treasurer map. It is something much more useful. A probability map. Instead of saying goal is here, the AI says, based on everything I have learned, this area deserves closer investigation. The difference is incredibly important. Science is built on evidence, not certainty. Responsible exploration is about reducing uncertainty, not by eliminating it. Every location highlighted by the AI still requires field verification. Geologists must visit site, collect rock sample, study the outcrops, perform geochemical analysis, conduct geophysical survey, and ultimately, if the evidence justify it, drills into the earth. Artificial intelligence doesn't replace any of these steps. It simply helps answer one of the most expensive questions in the exploration. Where should we start? This shift may sound simple, but its impact is enormous. Instead of exploring thousands of square kilometers equally, companies can focus their time, their people, their resources on area with the strongest geological evidence. That means fewer unnecessary survey, fewer unnecessary drill holes, lower exploration costs, less environmental disturbance, and better informed decisions. Across the mining industry, this approach is already transforming how exploration programs are designed. Major mining companies are investing heavily in artificial intelligence, machine learning, cloud computing, and satellite based Earth observation. Not because AI replaces geologists, but because it gives them a powerful new way to see patterns that were once hidden inside overwhelming amounts of data. And that brings us to the most important question of all. Can this actually work in the real world? Can artificial intelligence analyze satellite imagery, identify geological fingerprints, and highlight meaningful exploration target? There is only one way to find out. Let's test it. Not with the simulation, not with the animation, but with the real GeoAI system using a real satellite data to see what the Earth reveals. The experiment begins now.